back. In this lecture, we're going to start a journey, touring the most fantastic chemistry lab ever created, our environment. I'm going to spend the next 4 lectures trying to convince you that all those lectures ago, when I said to you that chemists study all things, I wasn't kidding. Matter makes up everything that we experience, everything that we discover, and everything that we are. And to prove it to you, we're about to go on a journey. The journey starts at the center of the Earth and will work its way outward as we consider the composition of our planet, its oceans, its atmospheres, and ultimately, the cosmos in which it resides. We're going to start with the interior of our own planet and discover the chemical explanations of why our planet has its magnetic field, why digging a hole in the ground looking for resources isn't always a very good idea, and we'll even see how atoms can move mountains. But before we can get to any of those things, first consider this. In the summer of 1883, in what was the Dutch East Indies, there was a volcanic eruption. Nothing new there. Volcanic eruptions happen all the time, all over the world. But this was no ordinary volcanic eruption. A chain of volcanoes making up much of the now Indonesian island of Krakatoa had been showing signs of instability for months. Frequent earthquakes and pillars of ash were observed in the months leading up to August of that fateful year. Now, on August 27, 1883, the island of Krakatoa essentially exploded in a series of 4 massive volcanic eruptions, the most powerful of which is estimated to have released the same amount of energy as 200 megatons of TNT. That is 4 times more energy than released by the Tsar Bomba, the Russian-made hydrogen bomb. That was the largest man-made explosive device ever detonated. To try to further put that into perspective, 200 megatons of TNT would generate about 230 terawatts of energy, or just about 10 times the global energy consumption in a year in modern times. So, if all of the explosive energy from that single eruption could somehow be converted into usable power, it would be enough to satisfy the modern world energy needs for about 10 years. That's every light, every vehicle, every furnace, factory, and refinery on the planet for a decade. Other more recent eruptions like this have occurred, most notably the eruption of Mount St. Helens in Washington State in 1980, which released only about 1/10 as much energy as Krakatoa, but still was enough to cause widespread devastation and claim 57 lives. But not all volcanoes are created equal. Where Krakatoa and Mount St. Helens erupted over a period of a few days, culminating with an explosion of devastating force, Mount Kilauea in Hawaii, for example, is currently undergoing an eruption that started in 1983. Now, although Kilauea has been deadly in centuries past, this most recent eruption is happening so slowly that the primary concern is damage to property and infrastructure like roads as the lava slowly creeps its way toward the Pacific Ocean. So, why so different? What is it that causes one volcano to ooze lava for decades, while another explodes violently in an afternoon? For that matter, volcanoes aside, why is it that some areas of the Earth produce huge fields of mineral resources, like the diamond fields of South Africa, while others are so barren of useful material that they remain uninhabited even today? Now, the answers to these questions all lie beneath our feet. Sometimes just a few inches within the soil, and sometimes many, many miles below. So we're going to change our focus a bit. In this lecture, we aren't going to look around ourselves for examples of chemistry at work. Today, we're going to be looking down, seeking out chemistry that happens not on the Earth, but within it. This lecture is all about geochemistry. The study of natural Earth systems is what we call geology. Now, geologists provide an invaluable contribution to our understanding of the planet. They try to understand the properties and interactions of materials within a planetary body, which usually it's our own Earth. But just like all other forms of matter, rocks and minerals also fall into the domain of the chemist. And it's often the chemical composition of these rocks and minerals that dictates their behavior in natural systems. It might seem hard to believe that something as simple as the atomic and molecular composition of rocks and minerals in the Earth can impact how mineral deposits form, volcanoes erupt, or even how tectonic plates move. If you're skeptical, my goal today is to change your mind as we take a tour of how chemistry drives the magnificent machine that is our planet. So let's get started. Here it is, the greatest chemistry lab ever created, our planet. But it didn't always look like this. About 4.5 billion years ago, the Earth was just forming. Chunks of debris from the proto-solar system were on the move, colliding with one another to create larger masses. These larger masses created gravitational eddies, which drew in more and more mass, ultimately creating planets. This process is commonly referred to as accretion, and it's generally accepted as the mechanism by which the Earth formed some 4.5 billion years ago. Now, think about this. Over several hundred million years, well over 1 trillion kilograms of material collided and smashed together to form the massive material that was destined to become Earth. All of those impacts carried with them great energy, which, through a combination of pressure, friction, and radiation, produced a rather hot planet. So hot, in fact, that it was entirely molten. In this hot, liquefied state, over geological timescales, the Earth slowly began to sort itself out by density. Iron and nickel, most notably, sunk to the dense metallic core of the planet. Lighter but still abundant metals like aluminum, magnesium, silicon, and oxygen as well, rose to the outer regions of the planet, forming what we call mantle and crust. Geologists call this process differentiation, and it led to a planet of non-uniform consistency, organized into layers with drastically differing properties. Differentiation's effects reach all the way to the very core of our planet. Nickel, being a bit more dense than iron, 8.9 versus 7.9 when compared to water at 1.0, that would be grams per milliliter. It's thought to be the primary component of the inner regions of the core. Now, this creates a very interesting situation, since nickel has a higher melting point than iron. And it turns out that the pressure and temperature conditions at the core, about 3.5 million atmospheres of pressure and 6,000 kelvins, are just such that the nickel inner core remains solid, while the outer iron core is molten. Now, you might ask the question, how do we know this? Did someone create a 4,000-mile-long thermometer and drill to the core of the planet? No, of course not. We know that the inner core is solid and the outer core is liquid because of the way that they transmit seismic waves created by earthquakes, volcanic eruptions, and even nuclear bomb tests. Now, beginning with this constraint, scientists then calculate the pressure at the center of the Earth using the information we have about its radius and mass. Now, under that pressure, maintaining liquid iron and solid nickel can only be accomplished under a very specific range of temperatures. Temperatures close to those present at the surface of the Sun itself. This is a rather fortunate structural feature of the Earth, having a partially molten core. Though not much more is known about exactly how the core behaves, it definitely has an observable effect at and even above the Earth's surface. The molten outer core decouples the core from the rest of the planet, allowing motions within these layers driven by the heat of radioactive decay of heavy elements. These motions in the iron and nickel-rich layers create a magnetic field, and this field extends far beyond the surface of the Earth, protecting us from harmful radiation from the sun and other cosmic rays. It also maintains a fairly constant orientation, helping us to navigate the globe. Now, the vast remainder of the Earth outside of the core is solid rock. In fact, all but the top 400 miles or so of what is known as the mantle is rigid, unmoving rock. And by rock, I mean a collection of silicate minerals, metals blended with silicon and oxygen in different proportions to create distinct minerals with varying properties. The phase behavior of silicate minerals is quite complex, but as a general trend, silicates that are rich in magnesium and iron, sometimes called mafic silicates, tend to be slightly more dense and have slightly higher melting points than do those rich in aluminum, potassium, and sodium, sometimes called felsic silicates. So just as with the core, as we move upward through the mantle, its composition changes as well, taking on a more and more felsic composition and less mafic composition until it reaches a critical point where the mantle isn't really all that solid anymore. The lower melting point of the felsic material makes it slightly plastic or able to flow over a narrow, several hundred-mile span of depth just below the crust of the Earth. So we draw another line within the mantle, separating its tough, rigid, higher iron and magnesium portion as the mesosphere, and the weaker, more mushy plastic region called the asthenosphere. In fact, the term asthenosphere comes from Greek terminology meaning weak layer. Now, the existence of the asthenosphere is critical to the geology of Earth's surface, as we'll very soon see. Without it, plate tectonics would not exist, and what we have come to know as slowly changing landscapes at the Earth's surface with drifting and sometimes colliding continents would be very, very different. Moving on to the final geological layer, we have the crust of the Earth, that outer layer of solid material that we call home. Although the term crust might invoke thoughts of very thin layers, the Earth's crust is, in fact, the only region of our planet that humans have ever directly explored. Our characterization of the core and mantle layers have all been determined not by direct observation, but by inference from seismic data and samples brought to the surface by geological processes like volcanoes. The crust itself, like the mantle, has a great deal of silica. But the identities and ratios of the accompanying metals are very different. Crustal rock is richer in aluminum, potassium, and sodium because of the silicate minerals that they comprise, and they're generally a bit less dense than others. Of course, there's still some magnesium and iron to be had there, but in less abundance than in mantle rock. Now, just as with the other regions of the Earth, we tend to find less dense materials higher up due to the process of differentiation. Continental crust is largely lighter colored, less dense felsic minerals like quartz, muscovite, and feldspar, while the crust of the ocean floor is more mafic in nature, comprised mostly of darker, denser minerals like olivine and pyroxene. So planetary accretion over hundreds of millions of years created this grand overall layered structure of the Earth, which we can rationalize based primarily on settling of materials due to density early in the Earth's life, differentiation. Now, that's fine. But when we look a little bit closer, we see that our generally sound method of reasoning out the Earth's structure by density starts to fail on closer inspection of more confined regions. For example, French scientist Alexandre Brongniart noted in the early 1800s that unusually dense iron and magnesium containing mafic rocks could be found in certain regions of the Alps. Brongniart's discovery meant that there had to be something more than just density dictating the composition of our planet, and it foreshadowed the greatest shift ever in the history of geological theory, that of plate tectonics. Now, until only a few generations ago, it was widely assumed that the surface of the Earth was a rigid, static, unchanging thing, that continents were in positions fixed since the creation of the globe. But the theory of continental drift, first advanced in 1912, challenged that old assumption and prompted geologists to contemplate the possibility that the continents actually moved across the globe and relative to one another, painfully, slowly, just a few centimeters per year. But it was enough to alter the face of the Earth over extremely long time periods. So the theory of plate tectonics was developed, an explanation in which continents and seafloors formed plates with defined boundaries. These plates ride along on thermal currents on the soft, plastic asthenosphere. And at their boundaries, these plates can spread apart, as they do at the center of the Atlantic Ocean, crash into one another, just as India and Asia do today, or slide along one another laterally, as they do at the San Andreas Fault in California. This model works remarkably well to describe why we see anomalies in the locations of rocks as Brongniart had observed. It also helps us to explain why certain volcanoes erupt so differently. The accumulation of less viscous magmas, richer in magnesium and iron, lead to long, lazy eruptions like Mount Kilauea. This makes sense since Kilauea is over a hot spot right in the middle of the ocean, whose floor is made from iron and magnesium-rich rock. But the much higher viscosity of felsic magmas are created in areas called subduction zones, where continental rock is colliding with seafloor. Of course, the seafloor itself slides under the felsic rock of the continent, but it also drags some of that continental material down with it. And this fills the magma chambers with thick, felsic magma that resists flow. This magma acts more like a plug, building pressure in the magma chamber until it's released explosively, as was the case at Krakatoa. Now, all of this grinding, colliding, and diverging over billions of years can cause rocks of greater density to be lifted up, and sometimes even on top of less dense ones. It can cause processes that mix silicates of differing composition in magma chambers beneath the surface. And it all adds up and starts to make sense when you consider plate tectonics. So, plate tectonics explains why Brongniart and others observed what appeared to be ocean floor-like minerals high in the Alps. And it explains why each volcano around the world seems to have an eruptive personality all its own. But where's the energy to move and mix all of that material coming from? Now here's where it gets interesting. Where does the planet get the energy that it takes to literally move continents? Of course, some heat was trapped during the initial cooling of the Earth as it formed, but to drive an engine so massive and powerful that it can move not only mountains, but whole continents, there has to be a fuel source which continuously provides slow, steady heat release over time. So how do you move mountains? You do it with atoms. You heard me right. The source of energy that created the Himalayas and the Rocky Mountains, that shrinks and grows oceans, and even drives titanic volcanic explosions like Krakatoa and Mount St. Helens, is the atom. It's been estimated that about half of the thermal energy given off by our planet is due to radioactivity and heavy elements trapped beneath its surface. Radioactive elements deep within the mantle of the Earth, trapped at the time of its formation, have been decaying and will continue to slowly decay, releasing a small fraction of their mass energy in the form of heat, which drives the grand machine that is our planet. We have trapped uranium-238 mostly to thank for this. This dense radioactive element accumulated in silicate minerals in the mantle some 4.5 billion years ago as the Earth accreted and cooled. And there it rests, at least about half of it, since U-238 has a half-life of just about 4.5 billion years. So, as this element continues to undergo slow alpha decay, it will continue to emit a large fraction of the heat that drives the convection in the asthenosphere. In essence, we're all riding through space on a gigantic nuclear power plant. Our journey from the core to the surface of the Earth is complete, but the discussion is far from over. Although the rocks and minerals that make up most of the mass of our planet have an incredibly complex chemistry all their own, they also play a critical role in chemical processes that involve our lakes, streams, oceans, and atmosphere. Rocks and the minerals that they contain are constantly being exposed to the surface and to groundwaters, reacting, dissolving, migrating, and even being redeposited in a very slow geological dance. This dance is partially responsible for the formation of mineral deposits that we all rely on for resources, but can also lead to environmental challenges and safety concerns. So for the rest of this lecture, let's take a quick look at the role that some rock types play in the chemistry that goes on all around us. Humans are resource-consuming machines. Our species takes the phrase living off the land to a whole new level. Not only do we rely on land to produce plants, we use those, of course, as food and building materials. Well, we go much further, digging deep into the earth in search of valuable metals like iron and gold. These mineral resources are extracted from the ground and chemically treated to produce the purest of materials for use in producing valuable material goods. But digging these materials out of the ground can come with a heavy price. Large-scale digging exposes large tracts of once subterranean Earth to the atmosphere, and that means exposing it to potentially reactive species like oxygen and water. A classic example of the unintended consequences of mining is what's commonly called acid mine drainage. The most valuable iron ores are those that contain iron oxide minerals, since these deposits tend to be large and very rich in the associated iron oxide minerals. But a second type of iron mineral can form alongside iron oxides. Mineral deposits forming in environments without sufficient oxygen might also produce iron sulfide minerals, most notably pyrite, also known as fool's gold because of its lustrous gold-colored appearance. Pyrite tends to be found in smaller quantities, and it isn't normally used as a source of iron. As mining for iron and other metals ramped up dramatically in the 1800s and 1900s in response to the Industrial Revolution, a rather large quantity of iron sulfide-bearing rock, generally considered a waste product, started to pile up in and around mines all over the world. The problem with this is that iron sulfide, quite happy underground where oxygen can't easily get to it, is now left in the open air, ready to react with oxygen and rain or groundwater. There are actually 3 important chemical reactions that go on that cause acid mine drainage. So let's consider each one individually and then consider them overall as a single process. The first process is the reaction of iron sulfide with oxygen and water to form iron 2 ions, sulfate and protons. In the second part of this process, iron 2 becomes reduced to iron 3+, which is the electrochemical driving force for this step in the reaction. It also makes some water. And in the final step of the process, that iron 3 reacts with even more water to form a compound called iron hydroxide and more protons. Now, what I'd like to do here is balance all of these equations so that we can add them together and see the overall process. So if you're up for a challenge, try to balance this chemical equation, but balance it for just 1 mole of FeS2. Now you can use fractional coefficients here if you need to because we're dealing in moles, not atoms. That's okay. But try to get a 1 in that FeS2. So go ahead and hit pause, balance the equation if you'd like, and I'll give you my answer. Here's mine. This is my balanced equation. A mole of iron sulfide reacts with 7½ moles of oxygen and a mole of water to form a mole of iron 2, 2 moles of sulfate, and 2 moles of protons. And similarly, I can balance my other 2 reactions for 1 mole of iron. So in this case, I've got these coefficients, and in my third reaction, I'll have these coefficients. Now, the interesting part is when we sum the process together, we can see exactly what goes on during acid mine drainage overall. And that is that 1 mole of iron sulfide reacts with quite a bit of oxygen and also quite a bit of water. And in doing so, creates a material that's ironically named yellow boy. Ironically because it's actually more of an orange or ochre color, but it's very visible, very easy to see when it's forming. And it's something that you really don't want to see when it's forming because when you see yellow boy, that means that you've also got 2 moles of sulfuric acid forming right along with it. So acid mine drainage creates not only a very noticeable, recognizable mineral deposit in the form of insoluble yellow boy, but also quite a bit of sulfuric acid, which is what makes it such a dangerous process to have going on in the environment. One example of how this reaction can be environmentally crippling is the Berkeley Pit Mine located in Butte, Montana. This copper pit mine operated from 1955 to 1982. The pit mining strategy involves excavating a giant hole in the ground, exposing the subsurface, and allowing miners to work in the open air. Now, at the time, it was considered an improvement over underground mining, since the risk of collapse was virtually none. During nearly 3 decades of operation, a pit 1 mile wide and about a 1/4 mile deep was dug into the ground. Now, digging that deep took them well below the water table, which allowed groundwater to flow into the pit. So naturally, the mine operators pumped that water back out quickly to allow mining to continue. No problem, right? But trouble started to brew when the mine was closed and the pumps were turned off. Suddenly, that groundwater wasn't being removed. It was accumulating in the mine pit where the reaction that we just investigated had plenty of time to take place. So this open pit slowly filled with water, which reacted with iron sulfide and oxygen to produce a highly acidic solution. What's worse is that this acidic solution has the power to dissolve even more dangerous metals, like arsenic and cadmium, which are found in trace amounts in the surrounding rock. Over the years, however, the slow leaching of these metals has created a mixture so poisonous that it's widely blamed for the death of an entire flock of snow geese, 342 of them, which had the misfortune to stop on the pit waters for a rest in 1995. This acidic heavy metal containing concoction is currently confined to the mine pit itself. So you might ask, what's the problem? I'm not a snow goose. Well, the real problem is that the level of this potentially deadly lake is rising. As groundwater continues to fill the pond, its level creeps closer and closer to that of the water table. And once that level is reached, the flow will reverse, and this lethal solution will make its way into the water supply of the residents around the area. So how do you deal with a problem like this? Well, there's really only one thing you can do. To prevent the reaction, you have to exclude one of the reactants. The iron sulfide trapped in the waste rock is impractical to remove, and excluding oxygen from a mine pit, which can reach miles wide and hundreds of feet deep, isn't practical either. So the best way to slow this phenomenon is to avoid exposure to water. This has been partially accomplished by diverting the flow of water away from the surrounding area, as well as the construction of a processing plant to clean contaminated pit waters and dispose of them safely. All great lengths that had to be taken because of the mining technique that was chosen. So let's sum up. In this lecture, we started on a 4-lecture journey that will take us from the center of the Earth to the stars. We started by thinking about the various layers making up our Earth, the features of the core, mantle, and crust, and how they came to be so different from one another. We saw how the densities of nickel and iron, as well as their melting points, lead to a solid, spinning inner core decoupled from the outer layers of the Earth by a layer of molten iron. Then we toured the mantle, which consists of large amounts of silicate minerals. We saw how a gradient in the types of metals included in these silicate minerals helps to explain the hard mesosphere and the plastic asthenosphere. Next, we took a look at the crust of the Earth. We saw how even the sea floors and continents continue to obey this overall trend of density sorting based on the types of minerals making them up. But we ran into some trouble when we started to look locally. We saw how sometimes very dense formations can be found high in the mountains of continents. So we went on a quest to understand how this could be happening. The answer, of course, came through continental drift and plate tectonics, the motion and collisions of surface plates as they ride on a moving asthenosphere, driven by convection of heat provided largely by the radioactive decay of heavy metals deep within the mantle. And finally, we considered how rocks at the surface of the Earth encounter new partners to react with, including molecular oxygen and water. And we saw one example of how reactions like this can have devastating environmental consequences, as they have in the Berkeley pit in Montana. So we've completed our short introduction to geochemistry, but we'll be learning even more about our environment over the next 2 lectures, which discuss the chemistry of our oceans and our atmosphere.